If you are also looking for professional certified structural engineering services or courses, then don't forget to check link in description of this video.
Guys, in this video, we are going to do our analysis and design of a complete underground water tank using SAP2000. So let's start. Now, before we move towards SAP2000 and start doing modeling, let us first understand how we get the dimensions of this underground water tank. So the dimensions are based on the capacity that we are going to have in our underground water tank. And today in this video, we will be designing our underground water tank for the capacity of 6,000 gallons. So based on this capacity, I have calculated the following dimensions, that I will be keeping the depth around 6.5 feet, length around 13 feet, and breadth around 10 feet. So using these dimensions, I can make sure that my underground water tank can store up to 6,000 gallon capacity of water. Now, as far as the thicknesses are concerned of wall and base, so we have taken these thicknesses based on the ACI code. Now, as far as wall thicknesses are concerned, so we have taken this wall thickness based on the ACI code of environmental structures, and using this clause, let me show you that it says that thickness of the non-bearing wall that do not receive the vertical stability from curvature shall not be less than 6 inches. So the code limit is that it should not be less than 6 inches, but what we have done in our case, we have kept it 8 inches. Obviously, we will be checking based on our analysis result, we will be checking if that's not sufficient enough, then we will be revising it and we will be moving towards either 10 inches or 12 inches. But for starting point, it's good to have 8 inches. Then base thickness, we have started our base thickness from 12 inches, and let's see it's passed or not. If it's not passed, then we will change it. So these were all about dimensions. Now let's talk about, now let's move towards SAP and start modeling the underground water tank. Then we will be coming towards loading. So guys, now let's start modeling our underground water tank in SAP2000. So first you need to go to File, click on New Model. Now as you click on New Model, a window will appear in front of you. Now if you want to learn in detail about this whole window, so you need to go and check out our Udemy course on SAP2000, in which we have covered detailed introduction to this window. So for now, I will be not going into detail. I will be sticking just to my project, that is underground water tank. So first I need to select my units, and for this project I will be using pound fit unit, pound as force unit, and fit as a length unit, and our material will be, default material will be from United States. Now I will be using for my underground water tank grid only template. Now since we are doing modeling of underground water tank, so number of grid lines should be 2 in X direction, number of grid lines in Y direction should also be 2, and in Z direction it should also be 2. Now if we talk about the this grid spacing, so based on the dimensions of underground water tank, we will be putting our grid spacing. So our length is of 13 feet, so X direction 13 feet, our width is of around 10 feet, so Y direction 10 feet, and our Z direction is of around 6.5 feet, so keep the Z direction 6.5 feet. Now click OK. Now once you click OK, so this window will appear in front of you. Now after this window appears to you, go to define and define your material properties. I will be using the default material property, that is, you can define new material property from here, but I will not be using this new material property option over here. If you want to learn about this, so go and check out our course on Udemy, SAP2000, whose link is given in the description below. So I will be sticking to this 4000 psi concrete for this project. Click OK, click OK. Okay, then go to section properties, define our section. No, we don't have to define frame section, we have to define walls area section. Go to define section properties, then area section. Now here click on add new section. Now if you want to again explore these all options, so go and check our premium course on Udemy, that is on SAP2000. So for now I will be defining my thick wall of 8 inches, wall 8, and its thickness is, now remember we have kept the unit as feet, so that's why we have to enter the value here in feet, that is 0.667. 8 inches is equal to 0.667 feet, and then same for bending. Now what this mean by membrane bending, so go and check out our course. So 0.667 feet, 0.667 feet, material name it's 4000 psi, shell thin, click OK, that's all. Now go to again define our bottom slab, that will be around 12 inches, slab 12, then keep the membrane in bending around 1 feet, 1 feet, 12 inches, 1 feet, and material name 4000 psi, shell thin, click OK. Now we will be also defining our top slab that will be of 6 inches, slab 6 inches, membrane 0.5, bending 0.5, click OK. Material name 4000 psi, click OK. Now once you have defined your material properties and slab sections, the area sections, now you are good to go and start your modeling. So guys, now we are good to go to proceed with the modeling of the walls. So for which what I will be doing, so I have to draw wall along the grid A, along the grid B, along the grid 2, along the grid 1. So first let us define the views for these grids. Right now I don't have, basically to draw the walls, basically I have to use this command, draw rectangular area, and for which I need to have their elevation. So basically we have to draw elevation along grid A, along grid B, along grid 2nd, and along grid 1. So what I will do, I will go to draw developed elevation. I click on this. Now as I click on this, it will take me to the XY plane, and here I have to basically draw my elevation. Let us go back to z equal to 0. Why it's not going? It has now gone z equal to 0. So now what I need to do, the next thing that I need to do over here is I have to draw the elevation along these all grids, for which first I will be drawing elevation along grid A. So I click on the very first here 0 point, then up till here. Now as I right click, so my elevation along grid A has been created, and I will name it grid A. Click OK. Now after that, now this is our grid A and I want wall over here, so I will go to draw rectangular area, select the section of the wall that is of 8 inches, and then click on the top left corner and then bottom right corner, and then our wall has been created. But right now you can't see any color inside it, just a boundary. So basically by default in SAP, fill is turned off. So we click apply. Now here you can see your wall has been created along grid A. Click OK. Now go to 3D view and check it. So see, we have made our wall along grid A. Now similarly we will be following the procedure for other grids and draw the all 4 walls. So I am doing it in a quick way. Draw develop elevation, then along grid B. Click over here, then over here, then right click. Now as you click right click, you will be on this view, then along grid B, name it grid B. Add a new name display, click OK. Now go to draw rectangular area, click the top left corner and then stretch it to bottom right corner. Your wall has been created also along grid B. Now for grid 1 and grid 2, again go to XY, go to draw developed elevation. Now I'll be drawing along grid 1. I will be naming it grid 1. Add a new name display, click OK, then draw rectangular area, top left corner, bottom right corner. Okay, then again go and check in 3D. Good. Now go to draw developed elevation, then grid 2, . name it grid 2, add a new name display, click OK, go to draw rectangular area, click OK. So now in this way we have created our all the 4 walls. Now our next step is to create the bottom slab and top slab, but before that we will be doing its meshing. And let's check its local axis, because the local axis are quite important as far as the applying load is concerned. If our all the local, basically right now if I talk about the wall that is along grid 2 and the wall that is along grid B, they're both what? They both z direction. Their z direction axis is inside the tank, and so we have to make sure that our wall A, that is along grid A and along grid 1, their local z direction should also be inside the tank. It will simplify our procedure of applying loading, and I will show you this once we come to loading. Basically we will rotate their local axis, their z local axis, and in this way all the 4 walls local z axis should be either inside the wall or should be either inside the tank, or should all be either outside the tank. We will explore this thing when we will come to loading. Let's first draw the top and bottom slab, and then we will be moving towards meshing of all the structure. So for bottom slab, what I will do, I will go to that's quite simple. I need to go to XY plane, and then in XY plane I need to select Z equal to 0 for bottom slab, and then from here I will be drawing bottom 12. You have to make sure that Z equals to 0 for drawing the bottom slab when you are selecting the bottom 12. So Z should be 0. So in the similar way we will be drawing this bottom slab. So our bottom slab has also been created. Now our next thing is top slab. Z equal to 6.5 feet. So select same command, draw rectangular area, select the section, that is slab 6, top left corner, bottom right, stretch up to bottom right, and you are done. So if we go into 3D, you can see we have completed our modeling of the underground water tank. Now the next quite important step is doing the meshing. That's the quite important step of finite element analysis, because otherwise we won't be having results. So what I will be doing into edit areas, divide areas, and divide areas. Then I will be using divide the object into maximum size 1 by 1 feet. I will be using this option, click apply, OK. So here you can see we have defined the meshing of 1 feet for whole the structure. Here you can see. Now what we will be doing, we have meshed our structure. Now we are good to go for loading. So guys, now let's talk about loading. So as far as underground water tank is concerned, so our walls will be subjected to water pressure from the inside face of the wall, and the earth pressure and surcharge pressure on the outside face of the walls. Now the thing is that how we calculate these loads. So as far as water load or soil load is concerned, so it's quite simple. You just need to know their densities. You multiply their densities with their height, with their depth, and you get the load in PSF. That's the simple funda. So here you can see the density of water in FPS system is 62.4 pound per foot cube, and then density of soil is 120 pound per foot cube. And we will be using lateral earth coefficient for the case of soil loads such as surcharge or lateral earth pressure. We will be using this K0 factor, that is at rest, lateral earth coefficient at rest condition. We will be using this factor 0.5. So let's calculate soil pressure. It will be what? It will be just simply 120 multiplied, as here you can see, 120 multiplied with the depth, that is 6.5, and into 0.5. That's how we calculate the soil pressure. Then if we talk about soil surcharge, so how do we calculate it? Basically we do take soil surcharge as 100 PSF at 200 PSF, and this soil surcharge is due to the ongoing traffic movement of vehicles, so we consider it as 200 PSF but and when we multiply it with 0.5, so it becomes 100 psi. Then same for the water, but in case of water, we won't be multiplying this lateral coefficient pressure, so it will be just a density of water, that is 62.4 into the depth, as here you can see. Okay, now if we talk about load combination, so basically we will be designing our underground water tank. We will see our result of underground water design results in three scenarios. The scenario number one will be when we have constructed the underground water tank, but we haven't backfill it. Means the soil we have not put the surrounding soil. It's just we have constructed it, and we want to just test this, that whether there is leakage or not. So we, at that point of time, there will be only water pressure. Then the second case is maintenance phase. In maintenance case, what happens? Your underground water tank is emptied, and there is soil pressure and lateral pressure. There is surcharge pressure and lateral pressure, but there is no water pressure. So that's case number 2. And if I talk about case number 3, so in case number 3, it's operation phase. At the same time, you will be having your water pressure, your surcharge, and your soil lateral earth pressure. Okay, so these are the 3 scenarios on which we will be seeing our result. Now if I talk about load factors that I will be using in this tutorial, will be based on ACI 350, because this is the code that we use for ACI. This is ACI code that we use for environmental structures, and I have taken this load combination factors from there. So for that we will be using I have used appendix 6 for ACI 350. Okay, so for that we will be using 1.4. For soil we will be using 1.7. For life we will be using 1.7. For water pressure we will be using 1.7. And we will further be multiplying these factors with the environmental durability factor. For example, when we will be doing the flexural, we will be taking out the flexural forces. So we need to make sure that these factors are multiplied with these 1.3. Okay. Similarly, for when we will be going for status reinforcement, so we need to make sure that our these factor should be multiplied with this 1.3. So that's how this is done. So when we will be going to SAP, you will see it how we use it. Then so now we are good to go and apply the loading. And I haven't mentioned one loading over there, that is soil, the gravity load of water. So our bottom slab will also be subjected to gravity load of water. That will be around the same 390 psi, but in vertical direction. Okay, so let's move towards SAP and start assigning the load. So guys, now we are good to go for the applying loading on our SAP model. What we will do, we will go to define load pattern, and we will start defining our load pattern. The very first load pattern that we will be defining will be of soil and soil lateral, and we will keeping its type as that, add new load pattern, but its self-felt multiplier should be 0, so modify load pattern. Now after that, what we will be applying, the soil surcharge. Okay, surcharge, it will be live, and add new load pattern. Then water lateral, add new load pattern, again it will be live, and then water gravity. So that's how we have defined our load pattern. After that, what we will be doing, we will be going into define joint pattern. And basically we define this joint pattern name because of our applying our lateral load. Okay, so first soil lateral, click on add new pattern name, then soil surcharge, then water lateral. Click OK. Oh, sorry, add new pattern name, soil lateral, soil surcharge, water lateral, modify its name, delete pattern, this water lateral, it's okay, water lateral, okay, add new pattern name, click OK. Now once I have done this, what I have to do now, I need to apply the lateral load. I'm going to apply lateral loads on walls. So what I'm going to do, first let me turn off these top and bottom slab. For which what I will do, I will go to select, I will go to properties and then select the area section, and I will just select the walls. I will click select, and then what I will do, I will say show selection only. So now in this way I can only see my walls. Now guys, here is quite important thing that you need to know right over here. Now here you can see, if you see the wall that is along grid A and the wall that is along grid 1, wall along grid A and wall along grid 1, their local z-axis is projecting outside the tank. And if I talk about wall along grid 2 and wall along grid B, so their local z-axis is projecting inside the tank. Now guys, if you want to simplify your process of loading, applying loading, and in one click if you want to apply the loads on all the walls, so you need to make sure the local z, the orientation of local z-axis should be same for all the walls. So either you project all the local z-axis inside the tank or all the local z-axis of the walls outside the tank. For my case, what I will be doing, I will be selecting this this wall along grid A and grid 1, and I will be reversing their local axis so that they project inside the tank. For which what I will do, first I will go to grid 1. So I have reached over grid 1. This is my grid 1. What I will do, I will select this. Okay, 3D. Here you can see I have just selected the walls. What I will do, I will go to assign, frame, area, river, local axis 3. Keep assigning the same global orientation. Okay. Oh, actually this part has also been done, so I need to Control Z. Now go to previous selection, remove this part, and now go to assign, area, reverse local axis 3. Okay, so now just this wall grid along A is remaining. I will go to navigation, grid A. Yeah, I got on grid A. I will select this 3D. I need to go to assign, area, reverse local axis 3. Let me turn on the fill again. Okay, now here you can see all the walls local z-axis is projected inside the tank. Now we are good to go and apply loading. So for which what I will do, I will first select the area sections wallet. I have selected all the walls, close. Then I will go to assign, I will go to joint pattern, and I will select the soil lateral. Constant will be, now in constant D, I will be putting my height of the tank, that is depth of the tank is 6.5 feet, and how I want to, basically since lateral load is applied on the height, so how I had to reduce it, the lateral load. So I have to reduce it by 1 increment. That's why I click this. Now what I do, I click over this, and basically why this is giving this is not giving me applying loading. Let me see. So guys, what we need to do, we need to select the walls one by one for applying this joint pattern data. So first I will go click grid 1. Okay, it's grid A. Select this, soil lateral, apply. Okay, then again for this, so we have applied on A. Let me check. I can't see over here. On which wall we have applied, let me see. On grid A applied, so let me go and check. Let me go and check that whether joint pattern data has been applied or not. I think so, it has been not been applied yet so far. What we can do, close this. Go to navigation, grid. So see, first we are applying on second grid. Click on this, go to apply, go to assign grid 2. So okay, go to assign soil lateral, replace existing if there is any, so it will be replaced. So see, we have applied. Okay, now again click on previous selection, water lateral, same for the water lateral, click apply. So we have applied again for the water lateral. Now go to previous selection again, for soil surcharge 0 over there and 1, because it will remain same throughout the length, throughout the height of the wall. Click apply. So for wall along grid 2, we have applied all the joint pattern data. Okay, what I need to do next is click OK, and now I need to go and select another wall. Basically I think so there is some glitch in this, it's not running properly, so I have to check it whether I'm assigning right or not. So it's 1. Now I have assigned on wall number 2. Okay, now for wall number 1, I click over this and then go to assign joint pattern, soil surcharge, apply, then soil lateral, it will be 6.5 minus 1, previous selection, apply. Then again 6.5 6.51, previous selection, apply. Okay, then soil water, now water lateral, previous selection, apply. Okay, so I have applied for the wall along 1 and 2 direction. Now I will click OK. I will go to now wall along A and B. I click over this, assign joint pattern, water lateral, apply. Now again go to previous selection, soil lateral, apply. Now again go to previous selection, surcharge, it will be 0 over here and 1 over here, apply. Okay, now I need to apply in B. It's 1, I need to go to B, where I can find it. No, it's 2, B, I want B. B, okay. I select this wall, I go to assign joint pattern, soil surcharge, apply. I go to soil lateral, again -1, 6.5, previous selection, apply. Then soil lateral, then water lateral, previous selection, apply. Okay, now close it. So we have applied the joint pattern for all our walls. Now what I will be doing, I will be selecting all. Now since I have made already there, all the walls have same local z-axis orientation, so I can select the wall number B, then I can go to select the wall number A, then wall number 2, along 1 I have to check now. This is along 2. Okay, this is along 1, no? Okay. Now if I go to 3D view, so you can see I have selected all the walls. Now I will go to assign, area loads, surface pressure, all, soil lateral. Now since we already defined height in that portion, so we just need to multiply the density with the 0.5 factor, and it will be 60 for the case of soil. By joint pattern name, I will select the soil lateral and I will click on 60. 0.5 into 120 is 60, apply. Now since our local z-axis was inside the wall and I want the soil lateral to be projected inside the wall, so I will click bottom. If I want outside, mean against the local axis, so I will click top, but for this I will click bottom. So here you can see our soil load has been applied. Now in the same way I will be clicking previous selection, I will be clicking surcharge, and surcharge value was 0.5 into 200, that was 100. By joint pattern, soil surcharge, apply. So that's our surcharge has also been applied. Now in case of water lateral, our load is against the local z-axis, that is outside. It will be projected outside the wall, so it will be 62.4 because height we have already mentioned in joint pattern. Water lateral, replace existing load, previous selection, click on previous selection, apply. So in this way we have completed the loading of our all walls. Now we can show all section. Now only our bottom slab loading is remaining, so we can click OK and we can go to select properties, area section and bottom 12. Okay, close, show selection only. So now I have to apply load over here. What I can do, I can go to again select, I can click on previous selection. So this is my bottom slab on which I have to apply gravity load of water, that is area load, uniform shell. It will be how much? It will be 62.4 into 6.5. It was around 390 or something. Let me see. It was 390 water pressure. As here you can see, water pressure was 390. So 390. Load pattern name, water gravity, click apply. Load direction gravity, click apply. Okay. So now we have completed the loading of our underground water tank. Click show all. You can also check the loading. Right now I can show you that how to check that loading. Show element load assign, area, click on soil lateral. Now here you can see at the bottom how much we are having. 390, that's correct. That's what we wanted. Sorry, water pressure was okay. I have made a mistake. I have assigned the wrong water pressure. It was 405.6. I have to correct it. So 390 was soil pressure. So here you can see soil lateral is 390. It's good. And then water lateral, it should be 405.6. It's correct. Okay, surcharge, it should be 200. It's correct. So the loads have been assigned correctly. Now what I need to do, and also check their direction. Surcharge is assigned the correct direction. Soil lateral is also assigned in the correct direction, and water lateral, oh, we have also made a mistake regarding the water load. We have to change the direction, which we haven't. So let's go and correct this. So what we have to correct, we have to correct two things over right over here. The very first thing is we have to change the direction of this lateral pressure of water, and then also the value of gravity water pressure. So that's the benefit of checking. What I can do, first let me correct the gravity load. No? So I will go to previous selection, and then I will go to assign area load, surface pressure, assign area load, surface pressure, assign area load, uniform shell. Instead of 390, what I will be putting 405.6, replace existing load, click OK. So that's done. Gravity water load has been updated. Now what I need to do, I need to select the walls again. I went over there, I select this wall, that is wall number 2, then wall number B, then wall number A, then wall number 1. So in this way I have selected all the walls. Yeah, correct, that's good. Go to assign, go to area loads, surface pressure all. Now since I told you this, that when we will be assigning load against the local axis, so I have to click the top. Basically what mistake I made earlier was I have selected the bottom in case of water lateral 2, but I have to select the top. 62.4 is fine, replace the existing load, click apply. Now here you can see your direction of water load has been updated and it's pointing outside. Okay. Okay, click OK. So now we have completed our loading part. Now we have completed our loading part. Now what next we have to do? We have to assign the support, soil support. Okay. Guys, before we proceed towards assigning the soil support, let us discuss these cases that we discussed earlier, that we will be checking result on case number 1, that is test phase, then maintenance phase, then operation phase. So these are the load combinations that we have to define in our SAP model. So first let's define the test phase. Go to define load combination, keeping the same name, copying the name from here, test phase, click copy, Control V. Now in this case what we are going to have, as I mentioned, test phase tank full without backfill. When we say tank full without backfill, so it means it will be having dead load, it will be having water lateral load, and it will be having water gravity load. So in test phase there will be only water lateral and water gravity and dead load. Click OK. But make sure you apply the correct load combinations over here. So as far as dead is concerned, so it will be 1.4 into 1.3. So it will be around, because we have to multiply this environmental durability factor. So it will be, let me open calculator, 1.4 into 1.3, it will be 1.82. So we have to put this value 1.82. Then water lateral, since water lateral is the life, so 1.7 into 1.3, 1.7 into 1.3, it will be around 2.21, 2.21. Similar for this water gravity, it will be 2.21. Click OK. Now let's define another load combination, that is maintenance phase. In this phase there will be no water pressure, just soil pressure. That it was around how much? 1.4 into 1.3, 1.82, 1.82. Then soil lateral is again dead, so 1.82 add. Then as far as surcharge is concerned, so it's live, so it will be 2.21. Click OK. Now the next case is operation phase. Copy, paste. Now for that 1.82, click OK. Soil lateral again 1.82, soil surcharge 2.21, water gravity 2.21, water lateral 2.21. So that 1.82, soil lateral 1.82, surcharge 2.21, water gravity 2.21, water lateral 2.21. Do you remember how we have got these values? We have used the appendix C of the environmental engineering structure as per ACI 350. Appendix 6, we have taken this factor from there. So these were the factor, and because we are dealing with environmental structure, so we have to multiply with the environmental durability factor for flexure, that is 1.3. Okay. So we have done this. Click OK. Now what we need to do next, we need to select the bottom slab. Select, go to properties, area section, bottom 12, close. So selection only. So this is the slab on which you have to assign your soil pressure. Now before assigning soil pressure, what I will do first, okay, I will fix this. Okay, later on we will restrain this. Let's first select all the walls, previous selection. Okay, go select properties, area section, bottom 12, close. Now we have selected our wall, and now what we will be doing, we will be going to assign area spring, and we will be keeping the stiffness of how much, basically your subgrade modulus, its value we have calculated over here. It's 40320. We have taken the bearing capacity of 1 TSF. 1 TSF we have taken the bearing capacity, and then based on this bearing capacity and taking settlement value 50 mm, we have calculated a subgrade modulus that comes out to be 40320. So it will be 40320, 40320, compression only. Now let's see the local axis of this. First turn on the local axis, then we will be coming to this. So its local axis is, it's above, it's in positive Z direction. Okay, means it's along its local z-axis is projecting, okay, along positive z direction. Close. Now go to assign area spring 40320 40320. Compression only. Area object face will be, now since we have to assign in the direction of the local, in the direction of this local z axis, so we need to select bottom and click OK. So we have assigned the spring. Now click OK. Now after assigning spring, what we need to do next, we need to restrain these ends nodes. Otherwise we will receive warning while doing analysis. We have selected these nodes. Okay. Show all. Just to make sure I have selected all the bottom nodes only, not top nodes. Okay. Go to assign, joint, restrain, fixed, click OK. Now we are good to go for our analysis. So go to analyze, click run analysis, select all these action to run, click run now. Now once our analysis has been completed, so now what we will see, we will look at the movements in walls and in bottom slab, and I will also show you the shear values for the walls and the slab. So first let's talk about the walls movement. Okay, so since in our underground water tank we have two types of walls, one is 10 feet long and another is 13 feet long. So first let us check the 13 feet wall. This wall is 13 feet long. So what I will be doing, I will be going to display, show forces, now we have we have two types of movements in ETABS. The very first in SAP 2000, the very first is M11 and the next is M22. If I talk about M11, so it's the movement along x-axis, and if I talk about M22, so it's the movement along y-axis. So if I talk about M11, so let's see its value. So we will be seeing the values against these three loads combination. So first let's talk about test phase. Click test phase, M11, click apply. So here you can see we are getting not significant movement as far as test phase is concerned in 13 feet wall along M11 direction. The values are closest to 0. Kip fit. The unit is kip fit. Here you can see the contour you can match. Now let's talk about M22 movement. So here you can see we are getting just few movement around 1.1 in this portion, and if we talk about other portion, so the value is closest to 0. At the bottom we have, however, around minus 2.33 and closest to minus 2.4 feet movement. So in M22 direction at the bottom we have, means along y-axis direction, along this direction we have movement at the bottom, that is minus 2 feet, kip feet. Okay, so this was the value for this test phase. Now let's go and check the maintenance phase. M11, let us first see the value of M11. So here you can see we are not getting significant movement in this middle portion. However, if we talk about the ends, so in M11 we are getting sufficient movement at the ends. That's around 1.1 feet kip feet or 1.2 kip feet. Not much significant, but there is some movement at the ends in M11 direction for maintenance phase. For M22, in M22 direction, we are getting a negative movement we are getting negative movement in the center. Its value is minus 1.1, and at the ends we are getting around 2.4, 2.5 moment kip fit moment values. Okay, so far we haven't gone moment values haven't gone beyond 2.5. Now let's go to operation phase in walls. Okay, for this 13 feet wall, M11, again there is no significant movement in M11 direction in operation phase. Similarly for M22 direction, there is no significant movement. So the greatest value of movement that we have so far found in 13 feet wall was around 2.5 feet something, kip feet something. Okay, now what we need to do next, we need to go and check the 13 feet long wall, 10 feet long wall. So you can check you can check it the same way as we have done for the 13 feet long wall. You can check for the 10 feet long wall in the same way. I have shown you how you can do that checking. Now let's go to slab. Now in slab, you can also check the movements in the same way in M11 direction. Here you can see in M11 direction under test phase, we are having around 2.2 kip feet in the middle, and at the ends we are having minus 5 kip feet. For M22 direction in test phase, we are having around minus 7, minus 6 kip feet at the ends, and in the center we are having, and it's negative, and at the positive movement we have at the center around 4 kip feet. For maintenance phase, M11, at the center we have minus 0.52, that's insignificant, and similarly at the ends we also have significant, because in maintenance phase there is no water load. Okay, so it will be better if we check on operation phase. So again on operation phase we are getting 2.23 kip feet in the center, and at the ends around minus 6 and minus 7 kip feet. And similarly for M22, here you can see we are getting around minus 6 to minus 7 kip feet at the ends, and in the center we are getting 4 to 3 kip feet positive movement, and at the ends we are getting negative movement. So that's how you can check the values of movements for slab and walls. Now if you need to check the value of shear, so you need to go to F12 component and apply. So here you can see there is no shear in the slab. Let's go and check the walls. So in walls the value is also not much significant of shear. So that's how you do the shear check. So guys, that's all for today.